types of crystalline solids. So solids, we divided all of matter into solids, liquids, and gases. Solids can be divided into crystalline and amorphous solids, and crystalline solids can be subdivided into three types: molecular, ionic, and atomic. And just to refresh, crystalline means that there's an order to the atoms or molecules. There's a pattern. And amorphous means without shape. There's no long-range order. It's just a jumbled mess, right? Like my son's sock drawer. They're not paired up and laid out in neat rows or anything. Well, actually, one son does that. He has a crystalline sock drawer. He folds his socks, and he stacks them, and they're stacked by type of sock. It's a little over the top. And then the other ones, you're lucky if the socks are even in their room, right? Completely disordered. That's more normal, huh? Amorphous, no long-range order. So three categories. And these categories of the crystalline solids are based on what composes the solid. So a molecular solid, it's going to be composed of molecules. An ionic solid, composed of ions. We talk about formula units. There's cations and anions. The formula unit is just the smallest ratio of cations to anions. And atomic solids are composed of atoms. That's not too hard to remember, right? We can kind of generalize some of their characteristics, like melting points, based on what holds those particles together. What holds molecules together in a solid? We just talked about the three kinds of them. Intermolecular forces. Some type of intermolecular force is going to hold those together. Intermolecular forces are relatively weak, and so molecular solids generally have low melting points. Ionic compounds contain ions, and what's holding the ions together? Ionic bonds. A sodium chloride crystal, like in this table salt shaker. A crystal of this is large enough that you can see it, right? If you look closely, it's a little cube. It looks like a tiny crystal because it is. And it's one array of alternating sodium ions and chloride ions, and sodium and chloride and sodium and chloride. And there are ionic bonds in all directions. It's held together by ionic bonds, which are way, way stronger than intermolecular forces. So ionic solids tend to have high melting points. And then we have atomic solids. These are going to be elements. Elements or mixtures of elements, because those are the only sorts of substances that have atoms as their smallest unit. And these are going to have variable melting points. Some things will have high melting points and some will have low. When we look at mercury, mercury is an atomic substance, but it melts at room temperature. Iron is also an atomic substance, but it melts much above room temperature. As I usually do, I kind of said most of this stuff. Ice is a molecular solid. Dry ice, solid CO2. They're held together by intermolecular forces, and they tend to have low to moderately low. There will be differences depending on how strong the intermolecular forces are. Changes in the melting point. Ionic solids held together by ionic bonds, high melting points. Sodium chloride melts at 801 degrees Celsius. Very high. Atomic solids, these are things like diamonds. You can get xenon to be a solid at a low enough temperature. All of these are composed of atoms. And these atomic solids can be divided further into different groups. Their melting points vary. So these can be, atomic solids can be divided into covalent, such as silicon, where the silicon atoms are actually covalently bonded to each other. And diamond does this as well. They're actually covalently bonded together. You can have a non-bonding solid, where the dispersion forces are the only thing holding it together. These are going to have much lower melting points. Covalent solids have high melting points because covalent bonds are very strong compared to these dispersion forces. And then we have metallic bonds, the sea of electrons. And these are going to have variable melting points. The covalent solids, again, I pretty much said all this. Diamonds are estimated to melt at about 3,800 degrees C. It's kind of hard to measure that exactly, but that's what we estimate. In a diamond, this doesn't look at all like the lead in your pencil, does it? And it costs a lot more too, doesn't it? It's composed of the same atoms. This is pure carbon. The graphite in your pencil is pure carbon. The difference is in how the atoms are bonded together. A diamond has the atoms bonded together in a three-dimensional structure, and graphite has more of a two-dimensional structure, and that makes it slippery and makes it spread out on your paper. Diamonds are not real good for writing on paper. They're good for writing on glass because they'll scratch the glass, not so much on the paper. Non-bonding, very low melting points. Xenon melts at minus 112. Very, very cold. Metallic solids held together by metallic bonds. This is the idea of a sea of electrons. Metals lose their electrons easily. And so I think of, let's say, iron. You got a bunch of iron atoms, and those are like, mom at home with the kids, and she sends the older ones out to play in the neighborhood, right? And so there's a bunch of electrons roaming the neighborhood, playing together and just kind of being around. The mothers in the houses are attracted to these children out there playing, and they kind of keep an eye on them. And this sort of holds the whole neighborhood together. An attraction between these electrons, not necessarily your electrons, but these electrons in general. It's more like communal living instead of just sharing your electrons with one other person. Mercury melts below room temperature. Iron melts at 1809 degrees Celsius. Gallium is a fun metal. It's a solid at room temperature, but if you hold it in your hand, the warmth from your skin will cause it to melt. I mean, it's really kind of crazy. A solid metal just melting because of your warm hand. So these are like the moms in their houses, and here are the children out playing. And so the electrons are free to move around, and we call it a sea of electrons, and there's an attraction between the positive metal ions here and these negative electrons. And this sea of electrons is what allows metals to conduct electricity, because electricity is the flow of electrons, and the electrons are able to move around. So identify each of these as molecular, ionic, or atomic. There will be a question like this on the exam, and these questions should be very easy to answer if you just stop and think about it for a couple seconds. So from our study of nomenclature, what kind of a compound is NH3? It's a molecular compound, right? It's got two nonmetals. They're bonded together with covalent bonds. So what are the units in this solid? Molecules, ions, or atoms? Molecules, right? So this one's molecular. How about calcium oxide? Ionic, right? It's got a metal and a nonmetal. This is a Ca2 plus and an O2 minus, two ions. Is it molecular, ionic, or atomic? Ionic. And how about krypton? That one must be atomic, right? The atomic ones are always going to be elements. This one can't be atomic because it's a molecule. And here we've got ions that are stuck to each other. This is ionic. So the atomic ones are going to be a single element. Any questions?